In this video, we're going to do a simple example of using proc mixed to compare the differences between two means and compute confidence intervals, 84% confidence intervals, and effect size. Now, we're going to use a simple example that really just has two groups, and in fact, probably the more appropriate test would be a paired t-test. But our for demonstration, we'll do this, and it should hopefully help you to understand what's going on and how to use the appropriate numbers when you're computing effect size and confidence intervals. So we're going to take a data set that has 20 subjects. The 20 subjects were under a blue light condition, 1000 lux, and those same 20 subjects on a different day were under orange light conditions. And we're going to see how well they did on the accuracy of a word pair test. Now, a word pair test was 100 word pairs. They learned them, and then later, about half an hour later, they were tested on whether these new word pairs that they're seeing matched the earlier ones that they had seen. So 50 of the word pairs were identical. They were presented randomly, and if they showed up, the person would say match to be correct. The other 50 pairs took the other 50 pairs that weren't included and scrambled them up and presented them, and those were non-matches. And the question is, how accuracy were they, and did that accuracy differ on performance based on the lighting conditions? So if we were doing a paired t-test, we would have two columns. We would lay out the data horizontally. In this case, this would be blue and this would be orange. Now, for proc mixed, we have to do it vertically, and so these values, 74 on down, were copied from this lower part of the list, 74 to 82, you can see. So I've got the same data laid out both horizontally and vertically for this demonstration. All right, let's do our usual mixed model. So we have subject, we have color as a repeated measure. We're going to use compound symmetry. The dependent variable is accuracy, because we're just using this column here. And the factor is color, blue versus orange. Our model is just color, and our expected means are just color. And we're going to compare the main effects so we get paired comparisons, even though we don't really need it in this case, but we'll see what happens. All right, so let's see what we get. All right, we have two colors. We're using compound symmetry. We have 20 subjects. Our information criteria is that. We notice that in our F test, there is significant difference between the two groups. Well, what is that difference? Well, we can kind of use the covariance. We have our covariance measure there. We'll come back to that. We have our estimates and accuracy. The blue light condition was 81.8 and the orange was 78.4. When we see our pairwise comparison, which is the same as our F test, was 0.012. Now, let's take a look at some of the things that come up with this. So here are our estimates as they were listed out there, 81.8 and 78.4. And we have a standard error and degrees of freedom and so forth. Now, I want to compute the standard error of the difference. That's what you would use in the t-test. You would take the difference between means divided by the standard error of the difference to get a t. And we calculate our standard error of the difference by taking the square root of 2 times, bigger, okay, 2 times C4. Notice the standard errors are the same because it's using a pooled standard error, not for each one of them. So 2 times C4, or 2 times 1.059, and that value squared, because it's the standard error of the difference. If you remember your t-test, the denominator is the square root of the standard error squared plus the standard error squared. So that's 2 times the standard error squared. And we get 1.49. Now let's come down here to our pairwise comparisons. Again, if you were to subtract 81 from 78, you'd get a difference of 3.4. And mix just does the thing twice, once comparing blue to orange and once orange to blue, and the difference is the sign. Now their standard error of difference is 1.223. Well, what the heck is that all about? Because up here we calculated it at 1.49. So if we want to know what is the actual, what standard error are they using, we know that if this is the standard error of the difference, it's the denominator of a t-test, because this mean difference divided by this standard error gives us a t, which notice is 0.012, which is identical to our f-test, which I don't have here. Let's see, it's right here, 0.012. So our f-test, all those they match. We expect, we're comparing two groups, we get 0.012. Now, the denominator again is the square root of the standard error squared plus the standard error squared. So if we can figure out the standard error by simply taking this value and dividing it by the square root of 2, because it's 2 standard errors, so we're dividing by 2, but the 2 is under the square root, so it's that. Now, this is how when you, in this case, you don't have to hack your syntax in order to get a comparison of a main effect. You do have to hack your syntax. Like this is an example from the Chow data where we had lens type year by lens type, and when we get the expected means, it's a year by lens type. We don't get this compare, so you need to add compare lens type adjusting for LSD. You just copy this down there and add lens type in parenthesis. And when you run this on the interaction term, then you will get your standard error of the difference. And then you figure out what your standard error is by dividing by, taking this number and dividing by the square root of 2. That gives you the standard error. And then you can get to your standard deviation. You can use this standard error for your 84% confidence intervals. And then you use the standard deviation, multiply this number by the square root of n to give you the standard deviation. Now notice this is 0.865, but up here we said it was 1.059. Why is it different and which one is correct? Well, if we look at our estimates of covariance, we get 14.9. We have 20. We can take the square root of that. We've done this before to figure out how to compute our 84% confidence interval. We take that number, take the square root of it, that's our standard deviation. To get to the standard error, we take the standard deviation and divide it by the square root of n, and that gives us the 0.865. So 0.865 is ruling here. 1.497 is incorrect. Now, what is 1.497? Well, this estimate is our within subjects variance. In other words, where we have taken out the between subjects differences, and we are looking, we've basically made our analysis a little bit more efficient. But to get the between subjects, if we didn't want to count the fact that we've adjusted for anything, we could add these two together to get a between subjects variance. So we have here 14.9 plus 7.45 is 22.42. Standard deviation, again, we're taking the square root of that. The standard error, we're dividing it by the square root of n. And that gives us 1.059, which is the standard error for the difference between these means. So, and this number is just the square root of that 2 times the standard error squared, and then that standard error squared. And that is how we would do the SED for the between subjects. Now, let's again just kind of step back and think about what we're doing here. We have up here, we are looking at computing the standard error with using just the within subjects. We want to adjust for the fact that we are using repeated measures. This is what we're talking about when we note in our sample size estimation that when we are looking at 2 values that are correlated with each other, we can save a few subjects. So we have our standard error. We use our standard error in the confidence interval. We take that standard error and we multiply it times the t, the 84% confidence interval t. That's t inverse times 0.16 times n minus 1. And we get a confidence interval of 1.265. Our effect size in this case is our standard deviation, the difference between the means divided by the standard deviation, again from this within subject component. So again, our effect size is based on the fact that we're looking at the differences, the effect size within an individual, not including the between. We could figure out what the effect size was if we had if we were considering all the data. So instead of 0.879, it would be 0.718. So it would be less. Now, we want just the within subjects. We don't want to use the between. So when you have done your analysis and you get this nice thing lined up here with estimates, don't come over here and use these standard errors to compute your confidence interval. That's a mistake commonly made. We don't want to do that. We want to use the standard errors from either estimating from compound symmetry or from coming down to our word pairs, pairwise comparison rather, and using the standard error of the difference and using our little formula where we take this number and divide by the square root of 2, because there's 2 of them in that denominator. So 0.865 we can get by pairwise comparisons, or we can get to it from CS diagonal offset. So in this case, we don't have to hack it to get at this standard error of the difference, these comparisons, to use this one. But if we have an interaction like lens type and year, which was 2 groups by the other, we have to hack it to get the paired comparisons. And then we can use the standard error that we get from here to compute our confidence interval. So it's the confidence interval either of those 2 ways. So, all right. Now, next thing. Let's see how that compares to the paired sample t-test. So if we're going in and we're looking at doing a paired sample, that's, again, now we're going to do accuracy versus accuracy orange. Analyze, compare means, paired sample t-test, our 2 means. And in this case, we get our statistics. Notice our p-value is the same as it was before, 0.012. The mixed model mixed model main effect is 0.02, the f-test. The t-test or the paired comparisons in the mixed model is 0.012. And if we do a paired t-test, it's also 0.012. This is why the simplest way to do this analysis is to do a paired t-test. But you're limited to 2 groups. Everything we're saying scales up when you have more than just 2 groups you're looking at, or if you have a covariate or something. We do all the comparisons exactly the same way in the mixed model. Okay, we'll leave this for a minute. Let's go ahead and do compare means and independent samples t-test. We have color, and that is, define our groups, 1, 2, and we're just going to do accuracy now because now we're doing that straight, that whole row. We're doing all the people that are blues, and we're pretending like they're not paired. They're not paired. We're treating blue and orange days as independent variables. See what we get. We look at our t-test here. Again, same means. Means are identical. Standard deviation, standard errors. Now this does the standard error for each one independently. But if we look down here, the standard error of the difference is 1.49. Let's go to our Excel sheet because it's laid out up there. Okay, here's our paired sample t-test. When we compute our standard error from this, we're taking the square root of this value plus, or not the square root, the square root of this value squared plus this value squared for the 2, and we get 1.497. That's our paired sample statistics. When we come down here and we find the standard error of differences, we come over here and divide that standard error of difference by our rule of dividing by the square root of 2, we get an SD of 0.867. Again, I guess this is the standard error of difference. It's not 1.497. it's 1.22345. That's the point. This is a smaller number when we have a paired t-test than when we get when we use the means. So in a paired t-test, when they give you the mean and standard deviation and standard error, they're giving you the means and standard deviation and standard error of the individual colors, not the difference between the colors, which is what this is. This is the difference between them. So the average difference is 3.4, and the standard error of those differences is 1.22, and the standard error there is 0.86. And if we come back up here, we see that matches our standard error as we get from the diagonal offset, our standard error of differences from this compound symmetry is the same here. What about the 1.497? Notice our values there is the same as our value from the Proc mixed model when we compute from the estimated means. In fact, notice that these means here are identical to the paired t-test. So 5764, 1.289. If you figure out the average standard error here, divided by the square root of 2, you get 1.059, which is what you have up here with the standard error of the difference. Proc mixed, if you went by this top thing, would give you 1.497. It is the between subjects variance. We don't want that. In fact, if we were going to do an independent t-test where we don't consider these guys matched, which is what we just did, same means, we get the standard deviation, we get 1.497, which matches 1.497, 1.497. This is the wrong way. Don't do it. It's an independent t-test, and it's not taking into consideration the fact that the people are related to each other. And what's more is the p-value is 0.029. It's worse. We're more sensitive when we do the within subjects. We get a p of 0.012 versus 0.029 because we're partitioning the variance. We're taking out we're removing the difference between subjects and just looking at within subjects here. This includes the wider noise based on different subjects. This one does not. So it's a much more sensitive test, and our effect size is, again, we showed up here, effect size is 0.88 using within subjects. So the effect within a subject, the change from a subject from blue to orange is 0.879 of standard deviations. It's not as big for independent. Even though the means are exactly the same, the variation is bigger. There's more noise, noise being the standard deviation. There's more noise in independent samples or between subjects. And we can get that estimate from our covariance parameter by adding these two together and get the total variance. This is how much variance is being taken out by the differences between subjects. This is the amount of variance by the differences within subjects. I hope this clears things up. When you get your output and from a proc mix, and you go to the estimates, and you copy this into Excel so you can do your graph, do not use these standard errors. You still have to figure it out. So for example, I have drawn a graph here, and the confidence interval comes from here. These are 1.223, and this confidence interval, no, it's not. It's 1.265. We estimate the standard error. Showed you how to do that from taking the standard deviation divided by the square root of n, or using this, the estimation of the standard error from here, by dividing this number by the square root of n, then multiply times the t, we get 1.265. And that when we draw this graph over here, those guys are being defined by these means. So it's very tempting to use these standard errors, but they are not correct. Do not use these standard errors in creating your confidence interval. You have to get it from the CS diagonal or down here from the paired comparisons. Using this one, using these green ones, using this, this confidence interval will match your LSD paired comparison. Using this confidence interval computed from that will not. I'm really hopeful that clears things up. See you next time.